Hey there, we're going to look at 4.5 today, analyzing graphs of polynomial functions. So we're going to look at two objectives here today. The first being that you will be able to graph polynomial functions and identify their zeros, and then be able to find the relative maxima and minimas of these polynomial functions. And this falls just under these two standards dealing with graphing polynomials and functions and identifying key characteristics of them. So let's hop right in. First with a property here, the location principle. It says that suppose that y equals f of x represents a polynomial function where both a and b are two real numbers such that f of a is less than 0 and f of b is greater than 0. So basically remember we've got two values, let's say between 2 and 3. And so if I do f of 2, so that'd be plugging in 2 to our function, right? Then that value came out less than 0. And if I do f of 3, that value comes out greater than 0. And so then what it means is that at least one real zero happens between these x values of a and b. Again, that would be our 2 and our 3. Okay? And so what we're looking at, so again, 1, 2, 3, we're looking at there's a point here and a point here. What has to happen in between? Well, it's got to at least cross once, right? Because if 1 is below 0, 1 is above 0, that's what we're looking at there. Okay? And so looking at example 1, it says determine the consecutive integers between which each of the real zeros of the function f of x is equal to x to the fourth minus x to the third minus 4x squared plus 1 is located, and then draw the graph. And so what we're going to do is we're going to set up a table. So x to the fourth minus x to the third minus 4x squared and plus the 1, and then we'll get our y values. And so remember, our location principle is going to help us find some of those consecutive integers between x will fall. And so we're going to start with 0. And again, if I plug in 0 for all this, I'm going to get 1 because, again, all these become 0 except for the constant. If I plug in 1, we're going to get 1 to the fourth minus 1 cubed minus 4 times 1 squared plus 1. So that's 1 minus 1 that cancels. This is negative 4 and plus 1, so that's negative 3. At 2, so again, we'll plug everything. 2 to the fourth minus 2 cubed minus 4 times 2 squared plus the 1. So we're going to get, that's 16 minus 8, so that's 8. That's 4, so that's another 16. So actually these 16s will cancel. We'll get negative 8 plus the 1 will give us negative 7. And then we go to 3. And so we're going to see 3 cubed, or 3 to the fourth, minus 3 cubed, minus 4 times 3 squared, plus 1. So what we've got 81 minus 27, and this is going to be 9 times 4 is 36, plus the 1, and so getting all that together, we're going to get positive 19. Let's go to 4 and just see what happens. So we're going to get 4 to the fourth minus 4 to the third, minus 4 times 4 squared plus the 1, and so we're going to get 4 to the fourth. 4 to the fourth is 256, minus 4 cubed minus 4 times 4 squared, which is again another 4 cubed plus the 1, and so that tallies out to 129. So this looks like it's growing forever. But what we see right here from 1 to negative 3, somewhere in between there, we see that we have a change of sign. We've gone from positive 1 to negative 3. So between 0 and 1 is one of our first changes here. We also see a second change when we go between negative 7 and positive 19. So the x values that go along with that, we're looking at between positive 2 and positive 3. Okay. Now, remember what we said the other day is that my zeros can be determined by the power of the highest degree, and so that's 4 in this case, and so I've only got 2 zeros so far, so there's probably a couple more that are sitting out there. So I'm going to go to negative 1, and so negative 1 to the fourth minus negative 1 cubed minus 4 times the negative 1 squared plus the 1, and adding all of that together, we're going to get negative 1. Now, my table's a little off because I went 0 way up here, negative 1 down here, but we're going to see that I jump from negative 1 to 0. So there's another crossing between negative 1 and 0. And so I'm going to go to negative 2. And so negative 2 to the fourth minus negative 2 cubed minus 4 times negative 2 squared plus the 1. So that's positive 16. This will be a negative, and this will be negative 8. This will be positive 8. This will be a positive 4 and a negative 4, so negative 16 plus the 1 at the end. And all that together is going to give us 9. And so we have another change between these two. And so there are 4 changes because there's also, that's not going to work. There's also this one to this one, right? From 0 to negative 1. And so that gives us our 4 cases, right? So between 0 and negative 1. And so my values is that they're going to fall between negative 2 and negative 1, between negative 1 and 0, between 0 and 1, and between 2 and 3. And so when we plot all these points on the coordinate plane, so we've got 0, 1, and then we've got 1, negative 3, and then we have 2, negative 7, 3 is at 19, so that's above the graph, so it's going to be way up here, and then 4 is super high up, negative 1, and negative 2, positive 9. And so what our graph ends up looking like, again, this is not a perfect sketch, but it is something like this. So again, use the table to your advantage to see what this graph is doing. And so here's a problem I'd like you to try. Pause the video here with this one. Determine the consecutive integers between which each real zero of the function fx equals x cubed minus 4x squared plus 2 is located, and then draw the graph. And so you'll see there's a graph below there for you to do this with. So pause the video and try this problem. And so let's set up our table. Here's our x. Here's our x cubed minus 4x squared plus 2. And we'll get our y's. And so again, start at 0 and then work your way up until you know this is definitely going in the direction of the end behavior. Again, think about your end behaviors. Our leading coefficient is positive. The degree is odd. And so we'll have opposite going in behaviors. The right side is going to go to positive infinity. The left side is going to go to negative infinity. And so plugging in the 0, obviously we're going to get 2 here for the y. When we plug in 1, we get 1 cubed minus 4 times 1 squared plus 2, so that's 1. Minus 4 plus 2, so 3 minus 4 is negative 1. Plugging in 2, we're going to get 2 cubed minus 4 times 2 squared plus the 2, and so that's 8. This will be a negative 16 plus the 2 is going to give us negative 6. We plug in the 3, we're going to get 3 cubed minus 4 times 3 squared plus the 2, and so it's going to be 27. This is 9, and so it's negative 36 plus the 2 is going to give us negative 7. We'll go to 4. 4 cubed minus 4 times 4 squared plus the 2. So this is 4 cubed, this is 4 cubed. They all cancel, so I'm left with just the 2. If we go to 5, just checking to see what it's going to do, if this will turn back or not. And so we're going to get 125. This is only going to be 100 here plus the 2. And so when we look at that value, we're going to get 27. So I think we're pretty safe to say that this is not coming back. Understand again your zeros. Remember, they're going to happen when the sign of y changes from one side to the other, either positive to negative or negative to positive. And so we've got one of the zeros sitting between 0 and 1. And the other one is when it goes from negative to positive, and that's going from negative 7 to the positive 2. And so that is my second 0. But this is an odd degree function, and so with odd degree functions, we have to have an odd number of real roots. Right now I've got 2 real roots, so we've got to find our third. And so we're going to plug in negative 1, and so negative 1 cubed minus 4 times negative 1 squared plus the 2. So it's negative 1, this will be a negative 4 in the middle, and a positive 2, and so it gets me negative 3. And if we look this 2 to this negative 3, that gives me my third 0 of this. And so graphing it up, again, we'll do the same thing. 0, 2, 1, negative 1, 2, negative 6, 3, negative 7, 4, 2, and then 5 is off the screen. And then at -1, we are at -3. And now I'm not going anywhere else because if we look at it, I just kind of start to connect these. We see that I already have my 3 crossings. I don't have any other crossings to go. And so my 3 zeros of this will fall between, the first is between -1 and 0, the second is between 0 and 1, and the last one's between 3 and 4. So that would be my 3 zeros of this with their consecutive integers. Okay? And so as we look at graphs, just remember max and min as we graph these. So if we look at x cubed minus 3x squared plus 5, estimate the x-coordinates at which the relative maxima and minima occur. And so we'll look at this function. Now, as we're doing this by hand, again, we want to graph these points so that we know where they are falling. So x and y, and we've got x cubed minus 3x squared plus 5. So again, I'm going to start at 0, which gives me 5, because again, everything with x will go to 0. So I'm here. We'll go to 1, and so 1 cubed minus 3 times 1 squared plus the 5 is going to give us 3. So I'm here. We'll go to 2, so 2 cubed minus 3 times 2 squared plus the 5, so that's 8. This is going to be minus 12 plus the 5 is going to give us 1. And then we'll go to 3, so 3 cubed minus 3 times 3 squared plus the 5, so now I'm back to the 5 again. So there was 2, 1, and then 3, 5. And so we see we get some type of shape starting to form here. The question becomes, is this going to touch the x-axis here, or is this going to stay above it completely? That we don't know at this point. We'd have to test some other values between 2 and 3 to get there, but I will tell you that with this function, it does not cross here. This piece is going to curve something like this, and then curve out to that point. So we'll plug in some negative values to see where it's going to cross on the left-hand side of the coordinate plane. So plugging in the -1, so we get -1 cubed minus 3 times the -1 squared plus 5. And so that is going to give us positive 1. And as we go to -2, -2 cubed minus 3 times the -2 squared plus the 5. And so that is -8. This is going to be a positive 4 with a -3, so it's -20. And then plusing the 5 will give us a -15. So I'm way down off the graph here. And this is not going to come back. Okay? And so that's where we're at. Now, you can use a calculator to check your max and mins to know exactly where they're going to occur. And remember, that's going to be using that second calc function on your TI-83 and hitting number 3, which is for a minimum, or number 4 for a maximum. And so remember, you want to set up your left bounds and your right bounds so that your bounds encompass any maxes or mins. And so the min here is given to us at the ordered pair. It's a little less than 2 comma, sorry, it's a 1.93 e to the -6. So this is basically 0. So this y-intercept is at 0, 5, and that is our local max. And if we do the min, again, second calc, go to number 3, which is minimum, box in where this minimum is, and we'll see that as we can guess, we don't have to, it gives us 2.000021, so that's basically 2, and then the y is 1, and so this at 2, 1 is my minimum. Again, we've talked about these TI calculators, especially the 83s, having some rounding error issues, especially when we do these calculator functions of calculating zeros or maxes or mins. It just has an issue finding those. All right, and so let's scroll on down. You could try this one as well. X to the 4th plus 3x squared minus 2x minus the 5. Again, find where those zeros would be. Again, do this more without a calculator. You could use a calculator to get some of the values, but I'd like to be able to see this by hand, not just you sketching what you see on the coordinate plane. And so the last thing we're going to look at is being able to graph polynomial models. We're going to spend a moment here on a couple of steps of this, but the weight in pounds W of a patient during a 7-week illness is modeled by the function here, 0.1 n to the third minus 0.6 n squared plus 110, where n is the number of weeks since the patient became ill. And so they ask us to graph this function. And so again, this is a little bit more complicated of a case. It's not terribly complicated, but I would go to Desmos or go to your graphing calculator to get the idea of this graph. And so that's what I'm going to do here. And so here's our graph. And so we're looking for where n is the number of weeks since the patient became ill. This one isn't asking necessarily to find anything yet, but this is a graph of it, and so we see that the y-intercept is at 110. We see it has a little dip as we get out towards about 4 weeks, and then begins to rise as we get to 10 weeks. And so to describe the turning points of the graph and its end behavior, now remember for this graph, the weight has to be positive, so I don't care about negative weights, that's our y-axis. Negative weeks can apply a little bit here, but as we can see, this model does not make sense as we go further into larger negative numbers. So the real turning point that makes a difference. And so where's the turning point? The turning point is somewhere about here. We can get our graphing calculators and calculate that if we were to use the calc function on our TI-83s. And so using our TI-83 to get this point is at 4,106.8. And so what that means is after 4 weeks, the patient will weigh 106.8 pounds at their minimum. So describe the turning points of the graph and its end behavior. The end behavior is that as x goes to positive infinity, the f of x will go to positive infinity as well. We don't really need to talk about the left end behavior because we're talking about a real life problem with the 7-week illness. Part C, what trends in the patient's weight loss does the graph suggest? It looks like during the first couple weeks they lose a little bit of weight, and then the last 3 weeks, so this is where week 7 is, they do look like they're gaining some weight back. The question is that when they get to the end of 7 weeks, are they going to stop this project or not? But the weight gain that this guy shows between week 7 and week 10 is not realistic to this model. Okay, so what does the patient's trend, patient's weight does the graph suggest? So they lose weight the first 4 weeks until the patient begins to gain weight. And there you have it. And the last question here is it reasonable to assume the trend will continue indefinitely? Well, again, if we look at this graph, the graph is going to continue trending upward, hard and heavy. So is this model really going to suggest out that it can go for more weeks past this? Probably not. So the answer here is no, because the trend is to positive infinity. Okay. And so this last example is similar to the one before. Again, use the function wisely, use your calculator wisely to get turning points to the best of your ability on those. I'm going to leave this example here just for the sake of time. Again, hope you have a great day. I hope this has been an easy lesson for y'all, and I will catch you tomorrow.